A GenAI app can look perfect in testing, then collapse when an LLM slows down. Latency spikes become timeouts, retries, exhausted workers, and frustrated users. In this lesson, we'll trace that failure chain and look at how to design against it. We've already seen two production failure modes: prototype architectures that become brittle under real traffic, and token usage that quietly destroys margins. Now we shift from cost pain to reliability risk. Even when prompts and economics look acceptable, slow or unavailable LLM calls can trigger timeouts, retries, cascading failures, and a poor user experience. Traditional API reliability is usually about controlling known dependencies: your service, your database, your network, and predictable timeouts. LLM reliability adds more moving parts, and several are outside your direct control. Latency can change with prompt size, generated token count, model load, provider behavior, batching, and network conditions. A request may also include retrieval, reranking, generation, validation, guardrails, and writes. That makes one global timeout too blunt. Reliable GenAI systems need stage-level budgets, fallbacks, retries, and clear decisions about what to skip, degrade, or stop. Average latency is dangerous because it turns a full distribution into one comforting number. An LLM service might average 2 seconds, while 5% of users wait 8 seconds and 1% wait 20 or more. Requests are not equal. Some prompts are long, some outputs are long, and batching can make one request wait behind another. Users do not experience the mean. They experience their request. That is why production teams track the tail, where frustration turns into refreshes, retries, support tickets, and extra load. To see that tail clearly, teams use percentiles. P50 is the median request. Half are faster, half are slower. It is useful, but it can make a system look healthier than it feels. P95 asks a tougher question: how slow is the experience for the slowest 5%? P99 goes further, exposing the rare tail where incidents often start. For LLM systems, that tail can be extreme, because token generation, queuing, model size, and retries amplify delays. Optimize averages, but manage P95 and P99 like user trust depends on them, because it does. Long-tail latency is the checkout line of an AI product. A 2-second answer feels smooth. At 8 seconds, users start wondering if anything is happening. At 20 seconds, many retry, refresh, or submit the same request again. By 60 seconds, the experience feels broken, even if the model eventually returns a correct answer. Backend success rate is not enough. For chat, copilots, agents, and support bots, reliability must include user-visible latency, because trust, conversion, and perceived intelligence all degrade while the user waits. The dangerous part is that long-tail latency acts like hidden traffic. A request waiting on a slow LLM still occupies a worker, a connection, memory, and sometimes a queue slot. As more requests get stuck, the worker pool has less capacity for new work. New requests wait longer, the queue grows, and that extra waiting becomes more latency. The system can saturate even when request volume is flat. The trigger is not more users. It is slower downstream responses, reducing effective capacity. Timeouts fail when we treat the whole request as one shared clock. A user may expect an answer in 10 seconds, but retrieval, re-ranking, the model call, validation, post-processing, and writes all draw from that same window. If the model quietly takes 9.5 seconds, the remaining steps may still run, but they cannot protect the user experience. A latency budget fixes this by assigning time to each stage, plus a recovery buffer. Start with the user-facing SLO, then spend that time deliberately across the pipeline. A single GenAI request is rarely one operation. It is a chain of dependencies. Retrieval may wait on a busy vector database or weak index. The model call may hit rate limits, GPU contention, or simply take longer because the answer is long. Guardrails and post-processing can add validation steps, sometimes even more model calls. Finally, downstream writes can fail after the costly generation is complete. This is why timeouts and retries need stage-level thinking, not just one end-to-end number. A global timeout is a useful safety net, but it is still a blunt one. It tells the system when the entire request must stop, not which dependency is spending too much time. Retrieval, the model call, validation, or a write can quietly consume the whole budget and leave no room to recover. Per-stage budgets make the contract explicit. Each step gets a limit, and the overall request reserves time for fallback responses, cleanup, and useful errors. The right numbers depend on the endpoint and the user expectation. Most timeout incidents are not exotic. They come from a few repeatable smells. One is no explicit client timeout, which lets a model call hang until something else breaks. Another is treating the user timeout as the only timeout, while background work keeps running. Retries can add hidden damage too. If each retry ignores the remaining deadline, latency and cost multiply fast. And without cancellation propagation, tokens, GPU time, and provider capacity are wasted after the user has already gone away. Timeouts need budgets, cancellation, and fallback behavior working together. Cascading failures are dangerous because the original problem can look small. Maybe an LLM provider or GPU server is slow, not down. But every slow response holds an application worker longer than expected. As workers fill up, requests wait in queues. Timeouts trigger retries, which add even more traffic to the same stressed path. Soon upstream services start failing, database connections are consumed, and endpoints that never called the LLM directly begin to degrade. The key lesson is to contain slowness early before it becomes system-wide resource exhaustion. Retries feel safe, but in an LLM system they can multiply failure. If a provider gets slow, clients may resend requests before the first ones finish. One user action can become 3 costly generations, all competing for the same workers, queues, and provider capacity. When many clients retry at the same time, normal traffic turns into a spike, latency rises further, and the feedback loop accelerates. The fix is disciplined retry design, clear deadlines, exponential backoff, jitter to spread attempts, and a retry budget so recovery traffic never overwhelms the system. Reliability problems rarely appear first as total outages. They show up as tail latency, growing queues, retries, and saturated workers. Instrument every stage, not just the final user request. Track P50, P95, and P99 latency by endpoint, tenant, model, provider, and stage, because averages hide the users having the worst experience. Separate provider latency from application latency, so teams know whether the bottleneck is outside the system or inside their own orchestration. The best alerts fire on leading indicators: timeouts, retry rate, queue depth, in-flight requests, provider errors, and cost per failed request before customers notice degradation. The core lesson is to design for failure before scale exposes it. Watch tail latency, not just averages. Set timeout budgets across retrieval, inference, validation, and writes. Isolate slow dependencies, because one LLM bottleneck can trigger retries, queue buildup, and outages. Next, we'll apply the same diagnostic mindset to GPU OOM, fragile self-hosted inference, and model drift.